All right, today we're jumping into a really cool corner of AI, the whole science of creating artificial data, basically from nothing. Imagine you could just dream up a perfect, realistic data set for any problem you're trying to solve. That's the dream, right? But actually doing it, well, that is a serious, serious challenge.
So let's just start with that fundamental question. How in the world do you create data that feels real? I mean, anyone can generate a bunch of random numbers, but how do you make them act like a real data set with all the subtle patterns and relationships you'd expect to see?
And then, here's the real kicker. What if that data doesn't just have to look real, but it also has to follow a very strict set of rules? This is where things get super tricky, and it's really the central puzzle that all these researchers are trying to crack. And that brings us to our first big idea. Generating a table full of random noise is one thing, but creating a high-quality data set where, say, column A has a real logical relationship with column F, that is a whole different ballgame. Okay, so let's get on the same page with a key term here, a constraint. It's really just a rule the fake data has to obey, and this example is perfect. If you're generating customer data and you create a record where the country is USA, then the currency for that record has to be USD. It's not a suggestion, it's a non-negotiable, hard and fast rule, and the AI has to nail it every single time. So how do you even begin to build a system that can understand and follow these kinds of rules? Well, it turns out there isn't just one way to do it. There are a few different design philosophies out there, different blueprints, if you will, and each one has its own unique pros and cons. Now, this is where it gets really interesting, because you've got two main camps. On one side, you have these transformer-based models. They kind of read a row of data like it's a sentence, learning how each word, or in this case, each column, relates to the next one. On the other side, you have graph-based models. They see the data completely differently, more like a network map, where each column is a city, and the relationships between them are the highways. Two totally different ways of looking at the same problem. And you know the blueprint you choose, and the engine you put inside it has a massive, massive impact on performance. And I'm not just talking about the quality of the data. I'm talking about pure, raw generation speed. For the longest time, one of the standard approaches was a diffusion method called DDPM. It's a real workhorse. But to generate a single batch of data, it could take something like 1,000 little steps. It's powerful for sure, but it is slow. But then, look at this. 20. Some of these newer techniques like flow matching have completely changed the game. A model using this new engine can get to a similar quality result in just 20 steps. I mean, that's a 50x speed up. It's not just an improvement, it's a total game changer. But here's the thing, a super fast engine is only half the story. You still have to solve that core problem of making the data actually follow the rules. And this is where the real art comes into play. Okay, so there are basically three ways to play this. First, you've got the bouncer. You just generate way more data than you need, and then, after the fact, you check everyone's ID and throw out the ones that break the rules. Simple, but man, is it wasteful. Then there's the personal trainer. This is more hands-on. You're actively guiding the model at every step, kind of nudging it and pushing it towards a correct answer. And finally, you have the native speaker, which is kind of the holy grail. You design the model so the rules are just part of its DNA. It can't help but follow them, because it's how it was built. And you can really feel the pride in that third approach from this quote right out of the source material. No masking/guidance tricks. The rules aren't an add-on or a clever hack. They are a fundamental, built-in part of the system itself. It's just so much cleaner. So where is this all heading? What's the next big leap? Well, even though these methods are great, if you look through the research notes, they're all pointing towards a next-generation solution. A smarter, more powerful way to guide these models. And that future has a name. Classifier-free guidance, or CFG. It's a really slick technique. Instead of just pushing the model in the right direction, it calculates both the path towards the right answer and the path away from it. Then it kind of blends those two signals together to create this really strong, focused push that guides the output without needing a whole separate model to do the steering. So the crucial point is, why is everyone in this space so excited about CFG? Well, the source documents call it the most principled way to do this, because it avoids all those messy post hoc tricks. It's expected to give the best results, and those transformer architectures we saw earlier, they're perfectly suited for it. In fact, one document calls it the highest leverage single experiment available for making these models better. I mean, when you see language like that, you know it's a big deal. Okay, so let's pull all these threads together. Because when you're actually building one of these systems, you're constantly faced with what you could call the generator's dilemma. You have to make some tough choices. This table just nails that dilemma by comparing two sister models. On one side, you have Diffutran. It uses that older, slower, but very mature engine, and its focus is on achieving the absolute highest fidelity possible. On the other side, you have Diffuflow. It's all about that new, 50x faster engine with the rules built right in from the start. Its focus is pure speed and elegant design. See? There's no single best answer here. It's all about balancing these competing priorities.
And that really is the heart of it. This entire field is one giant balancing act. The ultimate goal, the thing everyone is chasing, is the generator that can do it all. Create incredibly high-quality data that perfectly follows the rules and do it with lightning speed. Which leaves us with one last, kind of mind-bending question to think about. Once we crack this, once we can craft the perfect data set for any problem we can imagine, with perfect accuracy and following any rule we can set, what's the very first problem we should point this thing at and solve?